Welcome. In this video I'll discuss vertical stability of tokamak plasmas, and these are important because they are essentially present in all modern high-performance tokamak plasmas, and so there's a problem that the entire plasma can become vertically unstable and move upwards or downwards, and in the worst cases this can result in a major disruption, so-called, when the whole plasma hits the wall, and these have to be avoided in big machines because they could potentially put very large heat loads and very large thermal and mechanical stresses on the machine itself, due to the large currents that the plasma is carrying and the very large energy content, of course. And so these need to be controlled and understood. They're present in particular when you have elongated plasmas, so when you take a circular plasma and then you stretch it out, or you shape it very strongly. These plasmas are desirable because they have very high performance, but they also lead to greater instabilities, so the plasma becomes vertically more unstable and more difficult to control. There are some control strategies that are used. The most important is the passive stabilization, and these are essentially big metal plates which are inserted at the top and bottom of the tokamak, and these slow down the instabilities from microseconds to milliseconds, and this is a timescale that the active feedback control can then act and put the plasma back where it should be. So there's a combination of passive stabilization to slow down the plasma, and then active feedback to control and ultimately put the plasma where we want it to be. So I'll first introduce why this is happening. If we imagine that I have the center of the plasma here, and so we have the major radius out this way, this is like R and Z. And we're looking at a cross-section of the tokamak, so you can kind of rotate it around this way. We have a plasma. We have the plasma core here, for example, with a current running into the page, so a current IP. If you want to produce X-point configurations, for example, so for diverter power handling, or stretching the plasma with elongation, one way of doing this is to put essentially coils above and below the plasma, so like this, with the currents in the same direction. So these are basically IC for coil currents. These are coils, and now the magnetic field. I'll just draw in some different color to make this clearer. So there's a magnetic field around these coils, which, let's say, it's going around like, let's see, it's going around like this. So there's a magnetic field around the coils, and there's a magnetic field, of course, around the plasma like this. At some point here, this field here will cancel this field here. They're going in opposite directions, and you'll end up with a separatrix, it's called. So there's a line somewhere in here where this will follow like this. It essentially produces like a figure of 8 pattern. So here we have a magnetic field which goes around this coil. Here it will go around this coil, and then it goes around the plasma here. So it's a magnetic field line like this. Okay, this produces the kind of X-point shapes that are typically used in tokamaks, because this is then intercepted with a plate. So you have a target plates here, for example, and the heat leaving the core plasma hits the target plates rather than the wall. Now, unfortunately, we have here 3 currents. So you have the current in the plasma, and then currents in the coils. And currents in the same direction attract each other. So there's a force between the plasma and this coil, and between the plasma and that coil. So so the plasma is being pulled upwards by this coil, and is being pulled downwards by this coil. In balance, these two will be equal, and so the plasma can sit there. But this is an unstable equilibrium, because if the plasma moves downwards by a small bit, then the force due to the lower coil will increase, and the force due to the upper coil will decrease. And so the net force will be downwards, and the plasma will move even further downwards. So this is an unstable situation, because if we shift the plasma down, I'll try and draw this here. So we have the coils, top and bottom. So we have I coil, and now we shift the plasma down by a small amount, so it's moved from its equilibrium position. We've shifted it down some small amount delta. This is the plasma coil. Now the forces are downwards has been increased, because now we've shifted this closer, and so there's a stronger force between these two currents, and the force upwards has been reduced, because this distance got larger, and so a small downwards shift will lead to a larger downwards force, and so this is exponentially growing. And extremely quickly, this plasma will essentially throw itself against the bottom of the machine or the top of the machine if it goes the other way. So it's an unstable equilibrium, but because the forces are so large and the masses are so small, this can happen extremely quickly. So the forces, so we have sort of Tesla fields. So if you just say it's the B field times the current times the distance. So it's times sort of mega amp, 10 to the 6 amps, that kind of level, and then distance around the tokamak maybe something of the order of 10 meters, so 1 to 10 meters depending on the size. And so we're talking forces which are like 10 to the 7 newtons. These are the forces on in either direction here. Most of the time these are of course balanced, but we're talking imbalances in a very large force, and then the mass of the plasma, which is what is being accelerated by these forces, this is very small. So we may have a large tokamak, maybe have 100 meter cubed, so each will be something 800 meter cubed, but this will be something like jet. We have densities which are up to say 10 to the 20 per cubic meter, particle densities, times say deuterium, and then we have the mass, 7 times 10 to the minus 27 kilograms, and so this is something like 3 times 10 to the minus 5 kilograms. So it's a very small mass and a very large force. And so these lead to very large accelerations and very short times. So this imbalance happens extremely quickly. So the growth rates are around 10 to the 6 per second. So in a matter of microseconds, this plasma will hit the wall. So this would apply to any tokamak plasma, essentially that all tokamak plasmas should be unstable to this. And so plasma should last only a few microseconds before throwing themselves into the wall of the tokamak. And this is usually made worse by shaping the plasma. So in general, the stronger the shaping of the plasma, the more vertically unstable it becomes. And the reason why people do this is that elongation is good for confinement. And so it allows you to have a higher plasma current for a given Q, higher IP, so plasma current for a given Q. So Q is limited by magnetic MHD instabilities like sawtooth or Q equals 1 at the edge. And if you're typically trying to keep Q as 2 or 3 at the edge of the plasma to avoid NTMs or other large kink instabilities, then this provides a maximum to the plasma current. So by increasing the elongation, you can have a higher plasma current, which then typically leads to better performance, better confinement, without hitting this Q limit. Unfortunately, I say this generally makes the plasma more unstable, and so we're typically limited to about 1.8 for the elongation. So an elongation of about 1.8 is about the maximum, because otherwise it becomes too vertically unstable to control reliably. And you can see why this happens by essentially considering how you produce elongation. So what typically happens is you have again the Z and the major radius, You have the coils at the top and bottom, and then to produce an elongated plasma you have to put an extra coil here on the outside, or you might have two coils here which has a similar effect. But essentially you're producing a field which is pushing the plasma away, so it's in the opposite direction to the plasma current. And so we have here the plasma current, which is going this way. So we're producing a magnetic field in this coil, which is pushing this plasma away. So there's a force inwards from this coil, and the current's in the opposite direction. As before, there's a force upwards towards this coil. So these coils are attracting, and the net field. And if I try and draw the similar colours to before, so I have, let's see, blue coils around here, and okay, yeah. So I have some blue coils around these fields here. So I have these blue ones here, and let's choose a different colour for this one. So this field is going in the opposite direction. So we have a field due to this coil going out like this, and this is essentially pushing these field lines away, and so we're ending up with a longer, more elongated plasma. So the act of this coil is to essentially stretch out the field lines, stretch out this plasma, and produce an elongated plasma. But this adds to the instability, because if we now displace the plasma, so we have again the coils at top and bottom. We have the coil on the outside here. So here with these currents. If I now mark this as being the center equilibrium location, and we now shift this coil, say, downwards again. So sorry, shift the plasma downwards. Now there is a force. There's still the enhanced force downwards due to this coil. There's the weakened force upwards on this coil, but there's also now a force on this coil, and it's acting now as a downwards component. So there's a repulsive force downwards, and you can see that this force has a downwards component which adds to the instability, and so this outwards, so a repulsive force, and it enhances the instability. Because for a downwards component, it has the force between the coil and the plasma has a downwards component, and for an upwards shift, there's an upwards component, of course. So these extra coils, which shape and push the plasma, also enhance the instability of the plasma. So that's the effect of elongation. So stretching the plasma tends to enhance the instabilities. Then we can discuss how you might stabilize these effects. So talk about stabilization effects. So first is passive, and the second is active. So for passive stabilization, what's done is you have a plasma. Let's say you have a single null like this, because even in a single null, I should say that we have a coil down here. We still have a second X point, which is up here somewhere. So I'll just draw this in. So we have a second X point further up here, but this is away from the main separatrix. So in eta, for example, that has, although it's a single null plasma, there's actually a second X point, but it's usually inside the wall at the top, so it's far removed from the plasma. But there's still a coil at the top to provide this kind of vertical force balance on the plasma. As I was saying, the feedback stabilization is essentially a matter of putting metal plates. So it might be something like this, for example, or it might be underneath the plasma here, underneath the diverters. We have essentially thick metal plates which have a long penetration time for the current. And the idea is that these provide the passive stabilization, because as the plasma moves, say, upwards or downwards, the field at the coil changes, and this induces currents, and these currents push back on the plasma. And so the time scale for the instability is no longer microseconds, but it's the time it takes the field to penetrate into metal plate. So it's the resistive time of the metal plates, and that is milliseconds rather than microseconds. So there's now a resistive time, so a wall tau W, and a wall resistive time, at which timescale the field due to the plasma can penetrate into the wall and the plasma can move. And this is, as I say, it's typically milliseconds rather than microseconds. And this gives the control system time to respond. And so the second part is the active feedback. And this is essentially either on these coils. So you can adjust these coils, or there might be extra coils. So sometimes there's an additional coil which is closer to the plasma to enable faster feedback. So for example, if these coils are outside the vacuum vessel, then that will slow down. If you change the current in these coils, that will slow down the field penetration to the plasma. And so quite often there's an interior coil, so closer to the plasma, which is used purely for feedback, because that can change current quickly. And typically you just need a small change in current, but it needs to respond quickly on this kind of millisecond timescale to keep the plasma where it is. And this control system responds to a few different feedback signals. Often there are loops at the top and bottom of the tokamak, and there's a simple analog system which was used in early tokamaks, which is essentially just an op-amp, so looking at the difference in voltage between the two signals top and bottom, and then using that as an analog feedback system. Modern tokamaks have typically digital programmable control systems, and these respond to a whole load of different magnetic sensors around the outside of the tokamak, and essentially do some form of either very simple or in some cases quite sophisticated reconstruction of where the edge is, and then control the location of the plasma. So it can use magnetic signals. You can also use things like D alpha, so light measurements typically, so things like the edge location of the plasma. So there are a variety of different signals that can be used, but it's typically magnetic pickup coils. So measuring essentially magnetic flux. So the combination of an active feedback system using magnetic coils and other signals, combined with the passive stabilization of just big lumps of metal at the top and bottom of the plasma, is enough to stabilize these vertical instabilities, which would otherwise very quickly destroy the plasma. And this is now pretty routine. This is done and has been done for many decades.